All right, let's get started. Let me see if anyone asked any questions. Yeah, Andy, Shane, Mistrano, awesome. Nishan was here with us last week. Perfect. Okay, happy that you're back. All right, let's get going then. So talking about, we're going to cover obviously some methods to attach components to shafts. We can't cover it all. We have less than an hour. And literally the number of methods to attach to shafts, it's infinite. We can keep coming up with new methods hour by hour. So we're going to cover a few. We're going to be jumping around a little bit here and there. Just try to give you an overall good experience in relation to this topic. So sometimes we call them round components. You may have a round component that is not necessarily a shaft. A shaft is a round component, but it's fairly long in relation to the diameter of the shaft. So typically something like that you would call a rod or a shaft. You could also have a round component where the length is not as long as it is for a shaft. It's a shorter component, but it's still rounded, and you need to be able to attach to those as well. That comes up a lot. It comes up both in custom applications, which, if you recall, is the type of application that you design something and it'll be manufactured or fabricated only 1 to 10 to 20 times, perhaps, maybe, definitely less than 100 units, usually less than 10. That would be a custom application for like a fixture and a manufacturing plant, custom device that you're creating that only 1 or 2 is going to be manufactured, such as assembly machines, for example. Mass-produced component product is what you see every day, mass production products, right? So some of the principles apply to both, some do not, because for mass production, you want to be cost effective. And some of the custom approaches that are cost effective for custom applications are not cost effective for mass production. Okay, now there are a couple of aspects, and we're gradually transitioning into more detail. Couple of aspects to keep in mind is that there is whatever method you choose as far as attachment to something else. And then there's also the aspect of locating the component. Sometimes we want to attach a component, but we also want a feature to locate it. Maybe it's a component that is going to be removed throughout its lifetime by the user, and you want them to be able to reassemble it into the same previous location. So same location every single time. So you need to design in a locating feature. For sometimes you do not. Okay, and we'll get into more detail as we go. DFM is always very critical, and it is the design for manufacturability. Sometimes people refer to it as design for manufacturing. The way I learned it was design for manufacturability. To me, that makes a little bit more sense grammatically speaking, but both are mean the same thing, and they're both valid. DFA is design for assembly, and you may have already heard of DFX or be familiar with DFX. X meaning it's a variable, so it can be DFM, DFA, DF, whatever, designed for something else. Okay, ease of use. For example, you have a bicycle seat. The post of the bicycle seat is a round component, obviously. You need to be able to attach it, in that case, to another round component. But sometimes you try to make that an easy feature, easy to use feature, because the user of the bicycle may need to adjust the seat height. All right. Same thing like a wheel. You do not adjust the position of a wheel, but you do usually want to remove your front wheel, depending on what area of the world you live in. In my area, well, I shouldn't say that. In just about every area of the world, there can be theft. And if you're familiar with owning a bicycle and living in public places, sometimes you get your seat stolen or the wheel or the bike altogether. So bicycle wheels, the front ones are usually removable, so you can lock it up with the frame and not lose it. So let's jump on the internet real quick and have a look at that. So let me look up, let's see, let's do bicycle seat first. Post quick release. That's what I'm referring to. In this context, they call it quick release. Let's look up some images. So you may be familiar. You can see this one here, for example. That's a quick release. It's got a lever so that the user can easily release that lever, which in effect releases the clamping force on the tube of the bike, on the tube of the bike seat. That way, you release that, you're able to adjust the height or take the seat with you if you need to protect it. So that's a quick release. And the way you adjust, in that particular case, you see a thumb screw feature on the other end. I think all of you are familiar with this, but let's just cover all the bases real quick. And these designs have been around forever, but I just want to make sure you understand. And remember, looking at the world around us and studying it in detail, especially us mechanical people, right? Evaluating mechanical designs around us make us a better engineer. They stimulate the mind, they give you ideas, they increase the size of the toolbox, if you will. So you need to be doing this constantly, all the time. If you're not already doing it, I strongly encourage you to start doing it. If you didn't know this about the bikes, go grab a bike, evaluate everything in detail. It's not all about designing a bike. Everything, a large amount of what you see in a bike's design can be applied to fixture design, to robot design, to machine design, etc. So really quick here. Back here, you see a thumb screw. And you might be able to see that it's got features for your thumbs, for your fingers. They enhance the grip. You are able to hold that when it's released, not when it's tight. When the mechanism is released, you're able to turn that to tighten the grip or to loosen the grip. So you need to find the adequate point where it is not too loose, not too tight, so that when you apply the lever, it'll reliably and effectively lock the seat in place. Okay. Really quick, let's look at, I lost where we are here. We'll be doing some SolidWorks a little bit later. Okay, this is where I want to be now. Quick release bicycle wheel, and it's very, very similar. You can see that one, for example, and you see the similarities once again. There's a lever. And you see the knurled feature in the back. That's a good word that we should all know in mechanical design. So let me just write it down so that you are aware of this word here. Knurl. If you don't already know that, become familiar with that. Knurl. And there are straight knurls like this one. There are different patterns that you can apply to a surface in order to increase the grip when you interact with a human being, with a hand. Okay. So, oh yeah, we were talking about locating, right? In this case here, you can see that there is a method to attach this round component to a frame, and it is always going to be attached to the same place. So there's no need, well, there is a locational feature, but the locational feature there is fixed, okay? Because we always want it to come back to the same place. In the case of the other one, the seat, you want to be able to adjust the height. There is no locational feature in this case. So you can slide the seat up and down. Let's say, for example, this is not a bicycle, it's a machine instead. And you wanted to be able to drop this component always at the same elevation, at the same height, and then fix it in place. One thing you would probably do, which is very common, is design a shoulder into it. So shoulder, you have a round component. This is side view, looks like that. You can attach a shoulder, which is a step in the diameter. Okay, so over here, if we made this a little bit thicker, I'm just going to exaggerate it, and we had a larger diameter, stepping down to a smaller diameter, you would have a shoulder, and you could repeatedly reassemble the seat in the same place. Well, whatever component we're talking about. Okay, before we look at this video, we're gonna start doing some sketches here. Are you guys with me? What I wanna do, hi Xian Xing, how are you? No worries about being late, I'm glad you joined us. What I wanna do almost every session, if you were here last week, some people experienced, and this happens every time, and I know for a fact it happens with all webinars, any streaming, even YouTube, which is extremely reliable. I always see complaints in the chat room, not through the academy, but just any other webinar you attend. I can't hear anything, or the video is fuzzy. What's going on? Is it over? Sometimes people think it's over because they don't see anything anymore. So what I want to do here is I'm going to be running a poll from time to time to learn from your current experience, so that I can give feedback to the streaming company that I'm working with. So let's take a moment to do this real quick. If you would please respond to that survey on your right. Some of you saw it already, but please notice that I added another option at the bottom. So at the bottom, if you're having poor quality, please choose between poor quality, but you have a fast, reliable internet connection, or the last choice at the bottom is poor quality, but you're not sure of what the reliability and speed of your internet is. If you would do that, please. And in the meantime, I'm going to get this ready for us to move on. Okay. Let's see how my sketching abilities are doing today. All right, thank you for providing that feedback. You can see the results right there. It looks like most of us are doing good. No poor streaming for now. That's what I like to hear. And I'm running it at HD, high definition, which is optimally what we should be doing every time. But if a lot of people start having streaming issues, I can drop it to standard definition. It's gonna affect your quality, the quality on your end, but not this. It'll improve the streaming quality, but affect the resolution. All right, let's see what we're gonna do here. We're gonna talk about set screws and other things. Let's see. Actually, I just remembered something. I'm gonna find an image here. That's what I should have done from the beginning. Okay, give me a second while I search for something here, okay? I have a pre-designed image that has to do with this topic that we can refer to begin with. Just trying to remember where I put it. I believe it's under graphics. Hmm. You know what? While I find it, let me share something else with you here. Okay, 1 second. I think I got it actually. Ah, okay. Let's have a look at this. This is a good idea. This is a good starting point. It'll stop moving around in a moment. Bear with me. Okay. And I can zoom in a little bit more. All right. So you should be able to see that on your screen. If you can't read it, I'll read it for you. But obviously, we have a shaft there, and we have two different collars attached to it. Both of these have a threaded fastener that's being used to secure the collar onto the shaft. The one on the left has, if you can read that, it says SHCS. That's how we typically abbreviate socket head cap screw. And the shaft collar that you see there on the left is usually referred to as a clamping type, sometimes called a split collar. There are various names that we use, but clamping type, split collar, that kind of a name is usually used for these types. The one on the right is a slightly different approach. It's not split in any way, and I'll give you more details in that regard. But it uses a set screw. The threaded fastener is a set screw that you can see there on the top, and it's coming down, and when you tighten the set screw, it presses on the shaft, and that creates the joint for this design. The shaft there on the right, I don't know if you can read it. It says steel shaft, and it is hardened. So you can have raw material, raw steel, aluminum, whatever metal you're working with, that is as is, if you will, without any post thermal treatment of any kind. Thermal treatments and other treatments as well are used for hardening. So you can harden either the entire shaft, or you can harden the outside of the shaft only. That sometimes is referred to as case hardening. For a stainless steel shaft, for example, you would probably not heat treat the entire shaft, because you don't necessarily need the entire shaft hardened. Usually we need the outside shell hardened. So you could apply a treatment called case hardening for stainless steel. All right. And the challenge here is, what are the pros and cons of each of these approaches? And what are suggested improvements? So I'm going to leave it there for a moment, and let's talk about, let's see. First thing to notice is, in this design, we have attachment to the shaft, but not a locating feature, right? So let me take this design and shrink it a little bit, and let's look at it in more detail. And there's so much that we can say about this design as far as improvements and critique that we would spend more than an hour, but let's try it. Let's go as far as we can. So first thing is locating. What we have here is shaft and two collars. Well, I'm gonna draw it more like a side view rather than a section view. So you have the bigger collar there. You have the smaller collar on the right. I should try to be a little bit more accurate here. Okay, let's talk about the one on the right first. It uses a set screw, so it's got a threaded hole, and it's got a set screw, which looks like this. That's off center, but it's threaded on the exterior. It's got a socket drive where you insert an Allen wrench or a hex drive to turn it, and it's got some sort of a tip. Not all set screws are the same. And this is one of the things about being a good engineer. With more experience, you learn the differences between set screws, between screws, between thread types, between materials. It takes time to learn that. We here at the Academy, we put these programs together trying to gather all that critical information for you in one place. And we try to teach it in our certificate programs in a few weeks, trying to put it all in the same place so you don't spend years trying to gather this information as you gain experience. So different tips, and we'll look at some right now. We'll go on the internet and look at some tips. But usually, well, what I drew here is sort of probably a cone tip or a flat tip. And you can see that once you put that in there, it is going to be pressing on the external surface of the shaft. Sorry, I just changed the direction of the thread there. It's going to be pressing on the shaft, and that's how the collar is going to hang on to or hold on to that shaft. So I think right away you can see, or you guys tell me, will I open the internet and look for some set screws? There are some drawbacks to this design, to this approach. Think about what could go wrong here. Let's say this is a machine and it's exposed to some level of forces, and we want the machine and this attachment, this joint, to be strong and reliable. What are some issues with this particular approach? Think about that while I go to the internet. Not only think, but please type it in. So let me move this so I can see your responses. Okay, and I'm waiting for some suggestions from you guys as far as what may go wrong with that type of design if we leave it just as is. So while you do that, here's a set screw with a flat tip. You can see that. And as I mentioned, there are several types of tips. Move it up. So from left to right, you can see at least here there are 7 different types. Plain cup is fairly common. Knurled cup, you can see. Okay, we already talked about the word knurl, right? It's a texture on a surface. So here, obviously, this is not for a thumb or a finger to grip it. This is because the knurled surface is going to bite into the material. It's going to dig in and create a better hold. Okay, the third one is flat, probably like the one I sketched. We have oval as well. We have conical or a cone. In a cone-shaped set screw, if you can picture it, you tighten it, it's going to bite or dig into the material, much like the knurl does. But the knurl has a pattern. The cone is just a single conical point digging into the material. Half dog is pretty much just like a flat tip. It's shaped a little bit differently, but the surface that engages the other surface is flat. And you have soft tipped set screws. Sometimes this will come with like a nylon tip. I think they use different materials, but typically the set screw itself is metallic, but the tip is an elastomer of some sort or a plastic of some sort, so that it's a softer tip that does not mar or damage the surface. So let's see. Camila said, hey, Camila, good to see you here. The set screw can loosen. So I smile because Camila was in the program, in one of our programs already, so she may be cheating a little bit. She already learned this elsewhere. Just kidding, Camila. I welcome your input anytime. So let's go back to the sketch. Let's see. And yeah, there are a number of things that are wrong with this approach. And Camila is absolutely correct. One of them is that the set screw could loosen. We haven't talked yet about how to secure, let's say, secure the external threads of the set screw to the internal threads of the collar. Obviously, a screw is intended for you to be able to turn it. So how do you, when you want it to not turn, how do you prevent that? So there are a number of ways to do that. First thing is to keep it from turning or backing out. You will hear that terminology. A screw can back out when you don't want it to back out. First thing is preload, or sometimes called preload, sometimes called pretension. Oops. Preload. In this case, I don't think there's tension there. The screw itself is being compressed. So you would preload it, or you'll also hear torque it. You have to give it adequate torque. That's one thing. And there are charts in the internet, charts in machine design books and things like that, that recommend the amount of torque for a specific screw size, material, and things like that. So that's one thing. You need to have proper torque. But the other thing is, I mentioned this might be a part of a machine, right? So in machines, there can be shock, there can be vibration, shock and vibration, almost no matter what amount of torque you have, even if it's adequate. Chances are you're running the risk that it'll loosen and back out. So torque by itself may not be enough. So another method to set them in place, thread lock. We can use a chemical means. Make sure I don't give you the wrong terminology here. Like a company named Loctite. Thread locker. Let's see, thread locking compound. Yeah. So you can go the chemical route, such as this here. And this is a company, it's a very well-known brand, Loctite. They make super glue as well, so you're probably familiar with them. And they make different strength compounds. Low strength for tiny little screws, usually. Removable if you want to make sure that it's nice and secure, but still you want to be able to disassemble it. Or high strength if you're probably not going to disassemble it and it's a critical component that really should never come off. Maybe safety is at stake, the user safety or the equipment's safety is at stake. You would probably go with high strength. Wicking, I hadn't seen this one before, but you're probably familiar with the word wicking. Has to do with the surface tension effect. If you have a very thin straw, almost like a needle, and you dip it in fluid, you probably know from your studies, having to do with the surface tension of the liquid in relation to the surface, it's going to kind of grip its way up and it's going to go up the tube because it's pulling itself up. Okay. So one way to, I imagine, I don't know too much about this wicking type Loctite. I haven't used it myself, but it's probably very thin. It's not viscous. It's very, very thin liquid that even though you have tight threads connected to each other or engaged with each other, the viscosity is so low that this thread locking compound can work its way up in between the threads. I suspect that's what that means. Okay, so we have torque and we have compounds. That would be a chemical approach to it. And there are others. I'm trying to go fast so we cover everything. Remember, these sessions are kind of a good overview with a little bit of a focus on something, but we're going to be bouncing around because as I talk about these things, ideas pop into my head that I think, okay, they need to know this, they need to know that, they also need to know that. So our certificate programs are a lot more structured. These lectures are going to be a little bit all over the place, packed with knowledge, hopefully useful knowledge to you. So bear with me as I bounce around. We have torque and we have the chemical compound approach. There are also mechanical components, mechanical approaches to making sure that a screw won't come off. One that comes to mind, actually, sometimes it's best to just do a search. So hollow, let's see, maybe jam set screw. Let's see what comes up there. Yeah, that's the one I'm looking for. Okay, so you also see as we go that one of the critical, important things of being a good engineer is knowing terminology. We don't know it all, but if we know a lot of terminology, we can more easily, more effectively do internet searches and educate ourselves. So these are set screws in a way, but they're hollow and they're short. One way to use these is to use them as a jam nut, if you will, for another set screw. Let's see if they did that anywhere here. Okay, I don't see a picture for that, but keep this in mind. I'm going to sketch it right now. So these are hollow and they're shorter. Okay, so you probably have seen, let me move over this way. You have probably seen where you use, actually, see, I told you I would jump around. This will be easier to find. Jam nut installed. Let's see what comes up here. Okay, you probably have already seen this. You have a bolt and you have a nut to secure the bolt. And then you will sometimes see a second nut. It looks like a nut, but it's usually a little bit thinner. That's a jam nut. So you use the primary nut to achieve the proper torquing, proper preload on the bolt. And then you use the jam nut to try to keep the nut, the primary nut, from backing out, from loosening. Something like this here. So that's one mechanical way that we can apply to set screws as well, but it's a little bit in reverse. You have your threaded hole. You have some sort of a shaft or component you're trying to secure. So you will install the, I'm calling it primary, just I think that word fits, the primary set screw. And then you will install on top of that or above it a hollow set screw. And this, the primary set screw, of course, has a socket head right there. Okay, so I think that makes sense, right? It's sort of like a jam nut in reverse. So I see a question here. Um, before that, it looks like, wow, I don't know how to pronounce your name. Can I call you Jay? It looks like you typed in key. You are probably suggesting an improvement, I imagine, to this design, that we could design a key to secure it better. I think I'm not sure at what point you typed in the word key. I apologize. But then your question is, yes, okay. Then your question is, okay, what if we want to remove set screws after putting the compound? Okay, so that is why they offer different. What am I doing? I'm getting confused with the keywords here. That's why they offer. I lost it. But if you go back and look for thread locking compound, you will find the image that I showed you, and there are different types, different levels of strength. So if you want it to be removable, you would definitely use the removable type or the lower strength type. Okay. All right. So where are we? Okay, that's just one of many ways to accomplish this. There are also, see, the world of threaded fasteners is just huge. You can almost specialize in threaded fasteners. But I want to show you at least a couple more real quick. And I do have to hurry up. Time flies. Let's look for a couple here. Let's see, thread locking fastener. Let's see what comes up there. Images. Oh, notice one thing. Look at this, for example. A lot of fasteners you can buy with the chemical compound already applied. So you get the you buy this type here. The chemical compound is dry, but when you assemble it, it does what it needs to do, and it locks the fastener in place. I wanted to show you another type. Let's see if we find it here. By the way, there are also split washers. I tend to not recommend split washers. I think they're not, most types are not too effective in severe shock and vibration. So I would not go with split washers. Okay. Well, this one, for example, let's see, this kind of approach, how can I look for this? This kind of approach here that you see, oh, on the right, it looks like a split washer. Yeah, I'm a little bit scared of those. I've had bad experiences with those. You learn, sometimes you learn by trial and error. But the one on the left, the head of the fastener has a hole through it, and a kind of a steel or wire rope is run through that hole, and that secures, that keeps the head from turning. I want to show you, I don't recall their exact name, so I can do a search for that. Just gonna sketch it real quick so we can save time. But I've actually seen that approach used in spacecraft, all the way around a surface, or let's say we have a flat surface, and we have these. I just drew 8 sides instead of 6. All right, one sec. So I'll try to do this quickly. So imagine that's 6 sides. These are heads. A top view of threaded fastener heads. Okay. In this case, we have 3 in a row, and as I mentioned, that approach has holes going through the head. So you can route this wire through these heads, all of them at the same time. If you do it in the proper pattern, it'll keep them from backing out. So in this case, if we want to back out, we're looking at a top view. If we want to back out, or remove these screws, we would go counterclockwise. So we need to apply this metallic wire in a way that it keeps counterclockwise rotation. So in this case, it would probably be something like this. If we route it this way, you can see that with tension on this wire, the more you apply tension, the more counterclockwise they're going to go. If a screw wants to back out and go did I do it the other way? So sorry, I did it backwards. This would be the way not to do it. This is if you want them all to back out at the same time. I'm just making sure you're paying attention. All right, so let's try that again. If we don't want them to go counterclockwise, we would pull this way. Is that right? Yeah, that makes more sense. So now you can see the wire will be under tension, and let's say this guy wants to go counterclockwise. It can't. It's going to be, if we try to do it, it's going to tighten the other two in a way, and it just won't be able to back out. Okay, there are dozens of mechanical ways to secure screws. Well, let's go back to this image here. This right here. Let me move it down. Let's move and talk a little bit more detail about this one. Okay. One of the issues with this approach here, actually, let's look over here for a moment. Let's address a number of issues. So let's say there's no jam set screw in the back. One thing is that we have the tip of the set screw pressing directly on the outside of that shaft. Let me bring it back up. Okay, so we have the tip pressing on the outside of the shaft. There's something called marring. Marring is deforming or damaging a surface. So the more we tighten this, we're probably going to start to deform or indent the surface. There are times when that does not matter, and if it doesn't matter, you go with that. But there are times when it is a problem. Let's say this is a removable component. The user has to be able to easily remove and reinstall this collar. We're talking about this guy over here. This approach here. When you deform the metal like that, not only does it indent downward, but usually the material looks for somewhere to go. So it'll also create a little ridge or a little mountain all the way around. So if you're working with close tolerance components, meaning very little clearance between these two, such as you see in the right, the line that I drew on the left shows a lot of clearance between the collar and the shaft. The one on the right is a lot closer, right? That's just by accident, but this is what I'm addressing. If you have components that are close tolerance like this, you can see that deformation is going to be a problem when you try to remove the collar. It's going to get stuck on these hills that are there. So one way to avoid that, if that's an issue, would be to on purpose design a recess for the shaft at that location. So you would probably, or you could, have a step down right there, and then and then it looks something like this. So in that step now, the set screw would obviously go in deeper, and it would still do the same thing. It would still deform the material, but now the deformation is out of the way. You just, if you want to remove the collar, you back it out and nothing is affected, and you're able to easily slide the collar off. Okay, so that's one issue. Now, another issue, if we look at a side view, let's take the sketch here. Yeah, so something like a dent, an indentation, a dent. More accurately, it's called marring. And I don't remember, is this 1 R or 2 R's? It's probably just one. But look up marring of a surface, and you'll see the pictures and definition. Now, if we look at a side view here, I'm going to draw it a little bit bigger than that. You have the shaft. Let's say the color is green. Something like that. And the color, you've got the set screw. Okay, another issue is if we think tangentially in relation to the shaft, this shaft can turn because the set screw is just on the outside, on an outside curved surface. So that's why you see pretty often on motor shafts, you will see flat. If we have a flat, now the set screw, especially, you remember they're flat tipped set screws. The tip of the set screw can engage the flat on the shaft, and that's a better design all around. Now you have a flat against a flat. It's harder for the shaft to rotate in relation to the collar. Marring is not an issue because you will mar the flat, but it's okay. You can still remove the collar. It has no impact. So we're improving the design gradually. So from a side view, it could be, depending on what the application is, it could be that there should have been a flat designed into that shaft so that the set screw goes deeper. Okay, let me know if you have any comments. Now, set screws are used quite often. I was going to say oftenly, quite oftenly. Is that a word? They have their pros and cons, and they're suitable for some applications, not for others. Let's go into SolidWorks for a moment. It's almost 2:30 Pacific time. Wow. So, looking at this here, you can recognize these are motors. Specifically, these are stepper motors. We won't spend time talking about what that means or how they're different, but it's a type of motor. And you can see that the shaft of the motor, a lot of them come with a flat. The flat is usually intended for you to use a set screw to attach to the shaft. Now, once again, they work in some cases, especially if you have the right torque, the right size of a set screw, the right materials. You add chemical compound perhaps, or you have some other method to secure the set screw. In those cases, it can work. Pulleys, things like that, they come with set screws so that you can use this approach. Now, if you are designing something that has a certain level of vibration and shock, set screws, it's best to stay away from them. They will loosen up. Things will happen, especially if you're designing a precision type of equipment. If this is a motion system that needs to be fairly precise, the last thing you want is screws coming loose, pulleys or gears coming loose. They're going to introduce positional error into your motion system. So for that reason, I'm going to show you one approach that I've used that I tend to rely on quite a lot, actually. It's not always the best solution. Keep that in mind. Everything we talk about sometimes is suitable, sometimes it's not. It's for you and the team to make that determination. But what I do is I kind of reverse the approach. Usually, let me show you what the usual approach is. Let's see. Sets. What do I want to look for? Let's see. Setscrew pulley on shaft. Let's see what comes up with that. Okay, that's pretty good. So this one here, you can see that we're not talking about a collar, but the collar or the hub is very similar to what we already talked about, but of course a pulley is integrated into it. And you see the set screw right there. So that set screw is pressing on that motor shaft. We can't see it. There's probably a flat under there. Okay, so it's a very common method, suitable for some things, not for others. So in this case, you have the thread on the collar. What I have done with much success is reverse that. I have the thread on the shaft. Let me show you what that looks like. Now I'm showing you some of my tricks of the trade. So you have the shaft, and in that case, well, okay, let me draw it first. Let's say this is the shaft, the motor is over here, and you have the pulley. Let's say it is a pulley of some sort. This is going to be out of proportion, but hopefully you can imagine what that truly looks like. So it's a pulley, and you know the belt, timing belt kind of a thing would run on the pulley. So here's the hub of this pulley. Usually, as I said, threaded hole is here for the set screw. I do the opposite. Sometimes when it makes sense, I will have a clearance hole here, and I will have a thread fabricated into the shaft, typically all the way through. That is usually best. So now I take now, okay, one thing to keep in mind, if we just add a clearance hole on the pulley from the end view, just the threaded hole will look like that. If I apply a threaded fastener, the head of the fastener will look something like that, and it'll be pressing over here. It won't be pressing on a flat, it'll be pressing on two lines right here. So that's a little bit of a problem. We usually don't want to avoid that situation. So rather than doing that, we would design a flat over here for the screw head to sit down on a flat. Okay, I think that makes sense to you guys. So now you have a flat that the head can sit on, the head of the threaded fastener. It's got a socket drive, and the fastener can go all the way into the shaft. It can overshoot. It's okay if it comes out a little bit at the other end. That's not an issue. You can apply your thread locking compound, which would end up then in this area over here somewhere. I'm just going to represent it like that. You can still have thread locking compound somewhere in there. I have not had the need to do the following, but if necessary, I suppose it is possible to have the screw go all the way through and possibly even add another flat on this end and then add a jam nut. I'm running out of colors here. A jam nut to secure the other end. So the primary hold would be the engagement between the two threads right here. The internal thread of the shaft and the external thread of the screw or threaded fastener. That's the primary area. And if you remember, sometimes we add jam nuts and that kind of a thing. The jam nut would be secondary, could be added on the outside. I haven't had the need to do that. Usually, the initial part that I described works perfectly fine. Those, at least in what I've done, which is not, I'm not talking about heavy machinery. I have used this technique for medical devices. So medical devices, you don't have high forces going on. You have automation that has to be reliable, very high number of repetitions, and some level of vibration. Under those circumstances, this approach has worked very well, and it does not come loose. If you're working with heavier forces, larger forces, heavy machinery, that kind of a thing, you would not go with something like this. I just want to make that clear. Things to consider, and we're about to wrap it up. Let's see. You suggested a counter bore. Yeah, if you have enough of a surface, depending on the size of the parts, you could add a counter bore. I think what you mean is this. If, let's say, the outside, I'm going to exaggerate it, is much larger, rather than a flat, you can counter bore for the head of the fastener. That is correct. Couple of things to keep in mind. With this approach, you're now adding a mass that is not centered with the axis of rotation. I'm referring to the head of the screw, and however, whatever. Sorry, my mom's calling. I should have turned my phone off. Mom, can't talk right now. I was saying, if you're dealing with high speed of rotation, do not use this approach, because the center of mass has been thrown off. The center of gravity of that threaded fastener is not on the axis of rotation. So this thing is going to wobble. It's not going to be stable. So that's another reason, another scenario under you would not use this approach. A high speed of rotation, not suitable. And there was something else. Another thing is, a lot of these motor shafts, or any other shaft that you deal with, if the material is very hard, then it's harder to drill and tap through that material. Capable companies will do it. More experienced companies, or maybe any company that has enough knowledge, is able to drill and tap through hard material. However, it's a little bit more costly. Maybe it's okay, since we're talking about custom applications, not large quantities. Maybe it's acceptable, maybe not. But I have been told, but when I implement this approach, they point out, just keep in mind, the motor shaft is probably hardened. We're not sure if we can do it. They always tell me that we're not sure if we can do it, and then they always do it. So it works. But if you're dealing in a situation where the shaft material is just too hard, it may be inconvenient to drill and tap through the shaft. Another thing, once again, coming back to forces, if you're dealing with high forces in drilling a hole through a shaft, let me draw it over here. Drilling a hole through a shaft and then tapping it, you have weakened that portion of the shaft. It's a little bit weaker. So you have to determine if that's okay or not, if that's acceptable or not. All right, you guys. Do you have any questions, suggestions? It's been about an hour. I want to respect your time. And I can keep going for another 3 hours. I can talk nonstop about this stuff. But we do label these as 1 hour sessions, and I want to respect your time. There's a lot of other stuff I wanted to show you, but we didn't get to it. Questions, comments? As far as the split color, let me just draw that real quick for those of you that can stay a little bit longer. The design on the left, you can see that it's split. So now when you tighten that socket head cap screw, it's going to deform the collar. It's going to deform it in a way that the ID, the inside diameter, shrinks. That's what's going to grip the shaft, and you create your hold. All right, I'm gonna keep going, guys. I see that most of you are still with us, so I'm gonna keep going on this topic of just a few minutes longer. I do understand if you need to leave, otherwise hang out and stay with us. So I see a question. I don't mind answering. Let's do this. If you guys have questions that are not related to today's topic, stay till the end. I will happily stay till the end, stay late, and talk to you guys about other things such as programming books for servos, for servo drives. Okay, so stick around and I'll give you some feedback on that. But for now, I'm gonna stay on topic. So really quick, let's sketch a couple of split approaches here, just to complete what the initial goal of this lecture was. The one that is the clamp that is modeled there in SolidWorks that you just saw looks something like this, perhaps. Probably a counterbore and a threaded hole. Threaded holes, by the way, you probably already know this. They're usually represented by dashed lines, not this thing that I was doing. I just wanted to be even more clear. But you have a socket head cap screw here going through there, and when you tighten it, you're going to clamp and squeeze the shaft, right? Now, you will see different approaches, and a lot of this, whenever possible, keep this in mind. You should try to find out what exists already, what standard components are available. Standard meaning off the shelf. It's ready to go. I just buy it. It arrives 2 days later, rather than designing your own thing. Design for a component that already exists. Purchasing such a component compared to the amount of time you're going to take designing it, doing the engineering drawings, getting it fabricated and all that, there's no question. It's much better to go with standard components. But there are times when you need to custom design something. So this is the typical approach. Sometimes you will see them with the slit or the cutout going farther. That way, we are reducing this dimension here, where the majority of the flexing will take place. Okay. There are different types. I wanted to cover other types, but at least let me play this one video for you. Oh, no worries. I'll get to your question in a few minutes. Now, this is usually I play videos. I have a specific way that I play videos that works very well. You guys hear it clearly. I think it's flawless, but I'm going to try a different approach here. Is that what I was going to do? I don't remember. Well, let's do this. I wanted to point out this website over here. This manufacturer, for example, just to give you an idea of getting out of the box and thinking in, outside the box to find innovative, creative solutions to your design challenges. We usually think in terms of 90 degrees, a cutout here, a cutout here, a flat here, a round shaft with the axis perpendicular or parallel to this, orthogonal terms, like everything is at 90 degrees. One of the things that you can do to unleash your creativity is stop doing that. Do not constrain yourself to 90-degree geometry. Think outside the box. Think curves, angles, awkward shapes. Just get out there. So this company, it's only one of them. They're probably not unique, but it's a very good company, Fairlock. They came up, well, I don't know if they invented it, but I think this particular design is patented by them. You can already see here that the slits at an angle. So there's a slit that is parallel to the axis of the threaded fastener, and then there's another one at an angle. So when you tighten the socket head cap screw, it grips the shaft. It's very clever. The thing with these things, I think, is that after you look at it, you're like, well, yeah, that makes sense. That's no big deal. It's two slits. But keep this in mind, when it doesn't exist and you're coming up with these innovative ideas, it could be that a lot of effort and time goes into it, a lot of spark. So I think when we see simple solutions to problems, they're quite elegant, and a lot was involved in coming up with a simple solution. Wanted to point that out. I think, all right, let's see if this video will actually play. I'm gonna have to mute my end, otherwise I think you'll have feedback. But I'm gonna play the video. Let me know later if you hear the audio or not. I'm not sure if you will. One second, I have to mute this. If you don't hear the audio, we'll come back and talk about it anyway. Just briefly, because we're pretty much done. All right. Were you guys able to hear that? I'm curious. Was it video for you only, or were you able to hear it as well? The video only. Okay. All right. I'll work on that next time. I'll play it the usual way, which includes video for in the future. But I think after our conversation, you were able to follow what was going on and why the design is what it is. All right, you guys. Thank you so much. I'm gonna stay now. No YouTube audio. Okay. I'm gonna stay around. Stick around just for questions of any. I mean, preferably on this topic, because I think some of you will stay for Q&A, ask questions about the topic. But if you have questions about anything else, I'm happy to answer the best I can. Just a reminder, please ask your colleagues to join us. I think it's beneficial to those of you that are pursuing mechanical design or interested in transitioning into mechanical design. I think this series and what the Academy does is beneficial to that end. And once again, it's very helpful to us. One way you can support us is to look up the channel on YouTube and subscribe to it, and also watch the videos, well, whatever portions interest you, and like the videos and comment on the videos. That way the YouTube algorithm interprets that as there's interest in this material, there's interest in this channel, and they show it to more people. That'll help us make our efforts here reach a wider audience. So I would appreciate that. All right. In the meantime, Humberto's asking, is there going to be a recorded webinar replay? Yes. So the way it works, those of you that were here last week probably realized that a replay was automatically sent to you, I think a day later. I think tomorrow you will receive an email saying, here's the replay link. So you'll be able to replay the webinar. You'll be able to watch it exactly as it happened today. One issue that I have with that replay is that you're not able to fast forward. There are times when, you know, you learned the first 20 minutes, you don't want to go through that again. You just want to go review what happened 20 minutes into it. That particular approach doesn't let you do that. It's an excellent way to do it and see the conversation and the Q&A and all that. But the inability to fast forward, to me, is a little bit of an issue. So what we're planning on doing is, okay, so the answer is yes. Humberto, tomorrow you'll receive a replay link. It's only available for 48 hours. You'll be able to watch a replica, a replica identical to what happened today. What we're planning to do is, the next few days, take those videos and upload them to YouTube. In YouTube, not only, again, is it beneficial for us, for the Academy, to get the word out there, but you'll be able to look at an index. We're going to write, at 18 minutes, we talked about set screws. At 20 minutes, we talked about this. You'll be able to fast forward to those points if you're interested in doing that. That's okay, Humberto. Don't worry, I'm glad you joined us late, and you'll get to see the replica replay, and eventually we'll let you guys know about once these lectures, some of them, not all, will be uploaded to the YouTube channel as well. All right. Q&A, whoever wants to ask questions, please go ahead and type them in. Otherwise, I respect your time. We're over the hour, so if you need to go, it's totally fine with me. I'm going to start answering questions. So there was one about programming servos, right? Let me see. I lost track of that one. Any books for programming servos? Okay, so first thing that comes to mind is, what type of servo are you talking about? Because the common public, usually the non-engineering public, the people that get into toy robotics and RC planes, RC cars, that kind of a thing, remote controlled toys and vehicles and hobby-like devices and instruments. When they talk about servos, they're talking about what's commercially available. Those servos, that's how they call them, are pulse width modulated. Let's see, RC servo. So these guys, these kinds of servos, a lot of people call them servos because they are, in a way, they are servos. So are you talking about that kind of a servo, or let me see, or more of a real engineering industrial servo motor, which now we're talking about this kind of a thing. In engineering, when we say servo, we're talking about these guys. So both are acceptable. I just, to answer your question, I need to know which one you're talking about. Let me see. See you next week, Andy. For automation of machines. Okay, so this kind of servo that's on the screen right now. Industrial. Okay. No, I don't. I don't know any books for programming these guys. I'm sorry. In my experience, we tend to have control systems engineers that are available. Sometimes electrical engineers or programmers that will take care of the programming of the PLCs, the programmable logic controllers. I have not personally programmed a PLC from scratch and programmed servos and all that. I have not done that. I know how they work, the PID loops, the closed loop system, the encoders, all of that. I understand it all, well, most of it, but I have not programmed them. So I'm sorry about that. All that, huh? I talked for like 3 minutes about this, and then the answer is, I don't have an answer for you. Any other questions? When is registration for the next course? You're probably talking about the certificate program. That's a good, thank you for bringing that up. Right now, when you go to our website and you click on certificate programs, the registration is not open right now. We are going to open it probably in 2 or 3 weeks. So right here, upper left, this is registration closed for now. But in the meantime, if you haven't done so already, go to this page, click from the home page, you click on certificate programs, and you can learn all the details about the programs that we currently have available. There are 2 programs, and you can learn about them. But the short answer for you is we are in the process of scheduling those programs to launch again. And we're probably looking at about 3 weeks from now. We will update everybody. All of you are on the email list. You will receive notifications, and the website will be updated with the registration open. Okay? Any other questions? Let's see. Camila is saying Automation Direct. Oh, okay. I'm familiar with them. Automation Direct has some good reference material. Okay. So you had asked about PLC programming and stuff like that. So you guys check out automationdirect.com for some reference material. Thank you, Camila. All right, you guys, I don't see any other questions. Once again, my pleasure and my honor to work with you. I hope you got something out of this. We're going to be doing this every week except for holidays, and if I get a catch cold or something, I may have to cancel. So it's been my pleasure. Take care. Have a great Saturday. Have a great weekend and a great next week. And see you next Saturday. Take care.